It is 8:41. Am I audible? Cool, cool, cool. All right. Um, Looks like maybe unsurprisingly, attendance is starting to dwindle. Uh, that's all right. Week two. Um, yes. Okay. So some logistics things. Uh, there is a problem set out and a programming assignment out. I've seen a handful of submissions for each of those. Let me log into Brightspace real quick. Um, As a reminder, the problem set is due this Friday, which is the 21st, and the programming assignment is due 2 weeks from today. Both of them have a like an assignment submission thing open on Gradescope, so feel free to submit there whenever you're ready. And remember that for the programming assignment, you can like submit as many times as you want. So if you don't have um, the grade you want yet, you can sort of keep resubmitting until you get the grade you want. Um, and hopefully the auto grader should give you like some valuable feedback on how to fix things uh, if you're failing test cases. Um, yeah. The other thing, office hours. I think all of the TAs have their office hours posted now. My office hours are going to be Tuesdays, so tomorrow, right after class from 10 to 12 Eastern. Um, for if you can't make that time and you need help outside of any of the like regularly scheduled office hours times, um, and also maybe for the people watching the recording, feel free to email me and we can set up a separate time. I just figured I'd like block that off for people to just in general show up, um, or stick around or whatever. Uh, yeah, I think that's all I have for course logistics. Um, are there any questions about any of that stuff so far? I saw that there was a question in the chat about 4C on the problem set. Did that get answered? Um, all right.
I wouldn't
If
call it
not,
answered.
okay. All right. Um, yeah, if there's more confusions, feel free to like stick around after class or post it on Piazza or come to office hours or something of that nature. The goal of problem four in general is to sort of like walk you through implementing a stack using two queues. Um, and so 4C is asking about how you can implement the push operation based on what you've built up so far. Um, okay, so if there's any other questions, now is a great time to ask them. Otherwise, we will move on with course content. All right, great. So last week we talked about linked lists, stacks, and queues, and then we started talking about big O notation and like asymptotic complexity and stuff like that. In particular, I think we talked about time complexity. Um, this week I want to dive further into the complexity stuff. So we're going to talk about um, recursion and how to reason about the complexity of recursive algorithms. We're going to talk about space complexity. Um, and things that you can do to sort of improve the time or space complexity of recursive programs. And then we're going to go over something called the master theorem, which is a tool for computing the asymptotic complexity of certain kinds of recursive algorithms. Um, and then depending on timelines and stuff, we might start talking about trees, like binary trees and stuff like that, towards the end of the week. Also, a reminder that I am not going to be in town next week, so starting the week of the 24th. And so I will post some recorded, like pre-recorded uh, lecture videos about um, sorting algorithms. You are all encouraged to watch those in lieu of attending class synchronously. Or for those of you watching the recordings, I guess there's not much difference, except for the fact that you won't have to worry about attendance polls or anything like that for that week. So I'm just going to release a handful of videos and you can kind of watch them at your own pace, ideally before the week is up, so that the week after that, when I'm back, we can continue talking about things and everyone's all caught up and all that. Okay, great. So let me go ahead and, oh, this is not the one I want. Maybe it's this one. Okay, share my screen. Here we go. I'm gonna assume it's visible. Play. Okay, there we go. Okay, so like I said, I'm gonna talk about recursion. Uh, Before jumping into actual, well, okay, so first of all, I guess some of these things might be review if you've taken 264 or an equivalent like C programming class. Hopefully you have some idea of what like recursive functions are, um, and like how function calls work, at least on like x86 and ARM based architectures. Um, but and so if you do, this will be like some the first few slides here will be like light review. If you don't, hopefully this helps you kind of get caught up before we start talking about some slightly deeper things. Okay, so as part of this review, we can talk about the function call stack, right? So again, this is a lot of this is kind of architecture specific. A lot of this is how things work on like x86 or ARM, but if you understand how things work on those architectures, you will, I mean, that's kind of the vast majority of anything that you'll see in the real world. Just yeah, I don't know, don't expect like some random microcontroller that you're programming to sort of have the same semantics necessarily. Anyway, that's my disclaimer. Okay, so if you remember from our stacks lecture, we used like the we used the example of function calls as an example of a stack, right? So stacks are last in, first out. And the way function calls work is the most recently called function, like the last function that's called is the most recent one that returns. And so you can kind of model this idea of like calling and returning from functions with a stack. And it turns out that this is a very good model in that it is like somehow backed by the reality of what the hardware does or what the compiler does or whatever. So in particular, um, every function while it's executing gets a chunk of local memory called the stack frame, or sometimes I'll just call it the frame. And this memory has space for all the parameters and local variables that the function needs. So whatever like arguments it takes, whatever local variables are defined within the body. It also has some space reserved for information about the calling function, such as like the return address. Um, and all stack frames throughout the lifetime of a process live in a region of memory called the stack, right? So again, all of this is kind of statically declared, right? So when encountering a function call, when you call a function in C, the C compiler generates code to push a new frame onto the stack and reserve space within that frame for all of the function's local variables, parameters, all of the extra metadata that it needs or whatever. And when you return from a function, the compiler pops the current function's frame off the stack and then returns back to the calling function so that the new top of the stack is the stack frame of the function that called it. Um, if that is, I've said stack and push and pop and frame a lot. So let's maybe walk through an example, right? So here I have a bit of C code. I've got a function called foo that just does a computation. I've got a function called bar that does something and then calls foo. And then I've got main, which calls foo and then calls bar. So before our program initializes, right, the call stack just contains like this base level of like the operating system kernel, the C runtime, whatever, right? The program starts, main is our entry point. And so the stack frame of main gets pushed onto the stack. Here, main is not taking any arguments. Technically, I guess the compiler generates like the argc and the argv things for you. So I guess it would have like pointers in there for args. But oh, I shouldn't say parameters. I should say locals. It has two local variables, A and B, right? And you'll notice that these are known at compile time, right? And so when main initializes, we know exactly how much memory to reserve for A and B because it's just two integers worth of space on the stack, right? So that's 8 bytes or 16 bytes or whatever that might be. Okay, so then we start executing main. First, we hit this call to foo, and so we push foo onto the stack frame. Foo doesn't have any local variables; it has one argument x, and so we reserve space for that. And then we execute the body of foo, which is a return statement. The stack frame also knows where to return back to, so it knows it was called from that line int a equals foo3. So we pop foo off the stack and then return back to that line. Move on to bar. It's a function call, so we push bar onto the stack. Here we've got two arguments, a and b, and we've got one local variable x. We start executing inside bar. Then we hit the return statement. But before we can execute the return statement, we've got another function call. We push foo onto the stack. And this time, the return address is the stack frame knows that it needs to return into bar and not into main because it's a different function call. And so we pushed a different return address onto the stack. And so when we pop foo off, we return back to bar. And then we execute that return back to main, move on to the return 0, and then pop main and return back to the C runtime. It's like that's what the call stack looks like, right? It's maybe important to get like comfortable, at least like intuitively with what that means. So that later on when we talk about like the stack space that a recursive function takes up or something like that, you kind of have some idea of what that means or what's going on. So before we move on, does that make sense to people, or are there like questions about that I can help clarify? Right. If there's no questions, we can move on. So for something simple like this, right, we've got two functions and then main calls them and then one of the functions calls the other one. Sort of just looking at the code is maybe enough, right? Or we can kind of like walk through the call stack at every step or whatever. We can kind of reason about this pretty effectively just by looking at the code. But for something more complicated or for recursive functions or something, it's often better to have, or it's often more convenient to have this visualization that I'm going to call a call tree. So this is a tree. We'll talk about trees specifically, definitions and so on, vocab and whatever. But for now, hopefully you have some kind of like hand wavy sense of what I mean when I say tree, and in particular, what I mean is this thing on the top right. So the call tree is going to have one node for every function call, and or it'll have like a node for main, and then every function that's called from main will have a child node from main, and then every function that's called from that will have a child node, and so on, right? So we've got main at the root, main calls foo and bar, so we've got children for foo and bar. Foo doesn't call anything, so it doesn't have any children. Bar calls foo, so it has one child called foo. There's two copies of foo here. That is by design, right? Because foo gets called in two different places. So this is sort of this is sort of like a visual representation of what's going on here. And in particular, this lets you think about the call stack without having to explicitly draw it out at every step, right? Because the call stack at any given node is fully determined by whatever the path looks like from main. So if we're at the foo under bar, right? So there's like the foo on the right. Maybe there's a laser pointer I can use or something. I don't know. Well, I'm not going to play with that right now. Okay, yeah. So if we're at the foo on the right, the path from main goes main and then bar and then foo. And if you remember from the previous slide, that's exactly what the stack frame looks like at that call to foo, right? So we can think about, or that's what the call stack looks like at that point in the code. And so we can kind of use this like tree to think about what the call stack might look like. And again, that'll be useful when trying to sort of like diagram out the pattern of calls that some of our more complicated algorithms are going to make. Okay. I'm going to assume that's fine. Please yell at me or type in the chat or whatever if it's not. But I'm going to move on. Okay. Put that sort of primer on function calls in general done. And we can talk about recursion. So a lot of times you will see big complicated problems that contain smaller copies of themselves, right? So for example, to calculate the nth Fibonacci number, which I'm going to abbreviate as f sub n, we can use f sub n minus 1 and f sub n minus 2. Importantly, calculating f sub n minus 1 is easier somehow than calculating f sub n, right? It's a smaller problem. It's a smaller input size or whatever. To calculate the depth of a binary tree, we can use the depth of its children, right? The depth of a binary tree is 1 plus the maximum depth of either of its children. And right, we expect a child to be smaller than the entire, we expect like the child tree to be smaller than the entire tree. And so somehow like calculating this problem of calculating the depth, we can break down into like smaller problems. Another one you might have seen is like freeing a linked list, right? Of course, you can iterate through all the nodes and do that, but part of freeing the linked list, one step in freeing the linked list is freeing the linked list pointed to by head arrow next, right? So this is a smaller linked list, and in order to free the whole thing, we also have to free this smaller linked list, right? So it's another problem that contains a smaller copy of itself. So in situations like this, rather than directly solving the problem, we can use this recursive or like divide and conquer approach. And this generally has two steps. So first of all, we've got the base case in which we define how our algorithm acts on a trivial input. So in the example of Fibonacci numbers, we know what the 0th and 1st Fibonacci numbers are. We know what F0 and F1 are. There's no computation necessary. We just like hard code that to say those are 0 and 1 respectively, right? For our binary tree, we know the depth of the leaf node, right? That's 0. We don't have to do any computation. That's just sort of trivial. We know how to free the empty list, right? It's null. You don't do anything. It's a no op. Okay, so if we can define how our algorithm acts on something trivial, and we can define how to take a non-trivial input, break it down into subproblems, and then combine the results from those subproblems into a solution for our non-trivial input, then we can then we have an algorithm, right? You take something big, you break it down, and then you call the algorithm on those smaller pieces, which might result in breaking it down again, until you get a bunch of like little trivial things, and then you know how to act on trivial things, and so you just do all of that. And then you sort of combine everything back up, right? I guess for this, you have to like know that at some point it's going to, I guess this is why you have to say smaller, right? Because if the problem size isn't smaller, if it's just a different problem, then you might never hit the base case, right? You might never terminate. And so you need to know that in order for your algorithm to be correct, in order for it to work, you need to know that the problem that you're reducing it to is in fact smaller, and in particular is eventually going to hit a base case, right? You can take a discrete math class if you want to know how to prove that, or if you want to know how to like do that more formally or whatever. We're not going to talk about that. All of our things are, it's going to be pretty obvious that our recursion is going to terminate. So for example, we can compute the nth Fibonacci number. I'm going to use this as kind of a running example throughout the rest of these slides. So I figured I'd put it here. As I mentioned before, our base case is the 0th and 1st Fibonacci numbers, which we're going to set to 0 and 1 respectively. Our smaller subproblems for computing f sub n are f sub n minus 1 and f sub n minus 2. And then the way that we can combine them is just by taking those results and adding them together, right? That turns into the recursive definition on the left. So I've got int fib, which takes n as its input. First, I have my base case. If it's a trivial input, 0 or 1, then I just return the value associated to that trivial input, which in this case happens to be 0 or 1. Otherwise, I make two recursive calls. So I call it on n minus 1 and n minus 2. And again, n minus 1 and n minus 2 are both smaller than n. And so I know that at some point my problem is going to get smaller and smaller and smaller until I hit this base case, which is good. So I call it on n minus 1, I call it on n minus 2, and I get my two results, and then I combine them by adding them up, and then I return that, right? Hopefully the code for Fibonacci is something that you've all seen before. But if not, here's sort of how it relates to this idea of like recursive algorithms, right? Okay, I am going to step forward. So we can look at the call tree for an example invocation of this, right? For, let's say we're calling Fibonacci on 4. So here's the code again on the left. So fib4 recursively calls, 4 is neither 0 nor 1. So we're not at the base case. So we recursively call it on 4 minus 1 and 4 minus 2, which is 3 and 2. 3 is also not the base case. So it recursively calls on 2 and 1. 2 is not a base case. So it recursively calls 1 and 0. 1 and 0 are both base cases. So they stop there. They return 1 and 0 respectively, which bubbles up to the call to fib2, adds them together, and fib2 returns 1. So now we go back and we call fib1. That's a base case, so it returns 1. So fib3 returns 2. We go back to fib4. It calls fib2, which calls 1 and 0. They're both base cases. They come up, they return 1. And we've got 1 and 2. So it comes up to 4 and returns 3. All right. So this is sort of what the call stack looks like, or what the call tree looks like for our Fibonacci. Now we can ask a couple questions about this algorithm, right? Just by looking at this call tree, we can like try to understand these. So first of all, we can ask about like the time complexity of this algorithm, right? In like big O terms, or maybe just directly, right? Like how many calls does this take? And of course, we can just count up the number of nodes, right? And that's 1, 2, 3, 4, 5, 6, 7, 8, 9. That's 9 nodes, right? So it's 9 total calls to fib throughout the execution of this process. And then we can ask about the space complexity as well. And that'll turn out to be something like O of n, but we'll talk about it in a minute. Okay, so in particular, if I look at the time complexity, the total like time complexity of the algorithm is whatever the complexity of a single call is multiplied by the total number of calls that we make, right? Because every call is to the same function, so we just need to know how long it takes for one execution of fib multiplied by how many times fib gets called, right? Each function call takes roughly a constant number of steps, right? I'm omitting something here, but that's going to be an attendance poll in a couple of slides. So I'm not going to say anything about that, except what I just said, I guess. Anyway, each function call takes a constant number of steps for now, let's say. So a single call to fib is O of 1, right? It might take 1 step, it might take 2 steps, but we don't really care. It's all like the same up to a constant factor. Each call spawns 2 recursive calls. So we can kind of see that there's going to be something like big O of 2 to the n total calls. We'll see how to prove this later, but we'll get some kind of heuristics for it as well. So we can think about the total time complexity is O of 1 times O of 2 to the n. If you remember from our big O lecture on Friday, the order of the product is the product of the orders. So that's going to be big O of 1 times 2 to the n, which is big O of 2 to the n. Right, so the time complexity of this particular algorithm for computing Fibonacci numbers is exponential, 2 to the n. Okay, I guess this is the attendance poll. When I say each call is constant time, what assumption am I kind of implicitly making here? And for a bonus point that again is worth absolutely nothing except for like the pride and joy of having answered a question correctly. Under what circumstances would this assumption not hold? And what would the overall time complexity be under those circumstances? I'll give a minute for people to think about this. Maybe drop your answers in the chat, maybe say them out loud, or just talk about it. If one of them makes n to be 0 or 1, then we're returning values. Yes, we're returning values, but the return statement is still like one step, right? So it's either one step of returning something, or it's like one step of adding the two numbers together or something like that. So it's still roughly constant. Is the assumption that you will eventually hit the base case? That's not an assumption, right? We know that we are eventually going to hit the base case because we're starting with some finite input. I mean, that is in some sense like a thing that we have to know to be true for our recursive algorithm to work. But that's like that's not an assumption in the sense that it's like it's not it's always true. Like it is true here, right? Something like only positive values. Yeah, actually, that's a good point. This works for positive n. Single operation on n. Okay. The thing about positive things is actually true. I didn't consider that. If n starts negative, then it is never going to terminate. Single operation on n, I think, is essentially what I was going for here, which is that adding two numbers we're assuming is constant time, right? If our integers are bound to be like 32 bits or something like that, then that's fine, right? That's a single hardware instruction that just adds two 32-bit integers or 64-bit integers or whatever like the register size looks like. But if we're working with like big ints or something, then addition could potentially be an n squared operation or like an n log n operation or something like that, right? Because we might have like a 128-bit integer, like n might be enormous, right? And so the addition might be between like really, really big integers, which means that we're going to have to like break them into chunks and sort of like do this like add them like add the ones place, add the tens place, and so on, but in binary, right? So we would have to like actually do some work to add. And so yeah, the assumption there is that addition is constant time. Often that is a fair assumption to make. Sometimes it is not. For the bonus part of this, anyone want to think about what the time complexity would be if we assumed addition was, let's say, like O of log n, which I think is what it would need to be because you would do like one per digit or one per block of digits. Yeah, it would be O of log n. Log n times 2 to the n. Interesting. That is a very, very good guess. I don't think that's correct. It's definitely not n squared because we are at least doing 2 to the n, right? making something go from uh, constant to log n is not going to make the time complexity any better, right? So it can't be n squared, it can't be n log n because 2 to the n grows faster than all of those. Log n times 2 to the n is probably the closest. However, you might notice that n here is not always going to be the same, right? We start with some really big n where log n is going to be some like non-trivial value. But as we sort of like recurse down, n gets smaller and smaller. And so log n doesn't stay the same throughout every call, right? So it's like log n and then plus log n minus 1 plus log of n minus 2 plus log of n minus 3 and so on all the way down. So it turns out to be a little bit more complicated than that. We will see that the master theorem can help solve recurrences like that. That was my pitch for the master theorem, which we'll talk about next, probably like tomorrow or the next couple of days or something like that. Cool. Yeah. Anyway, that's the attendance poll question. It's up on Brightspace, so you can go answer it now, or you can wait until after class. I don't really care. I'm gonna move on. All right, we talked about time complexity. Let's talk about space complexity, right? Fib, like we're not allocating any input dependent memory here. But because it's a recursive function, we do have to worry about the implicitly used space on the stack, right? Throughout like multiple calls to this, or throughout like recursive calls to this function. And so we can think about like the total space that this uses is whatever space allocated by a single call multiplied by the maximum possible number of stack frames. Like I said, we don't allocate any input dependent memory, right? We're not allocating like an array of size n or anything like that. So the space complexity of a single call is constant time, O of 1. Again, right, this is assuming fixed size integers. This could be, right, in general, if our integers get arbitrarily large, we would need log n space to store them. The maximum recursive depth is the depth of the call tree. And so you'll see like the maximum chain of recursive calls would be like fib of n calls n minus 1, which calls n minus 2, which calls n minus 3, all the way down to 0. And so the maximum depth is in fact going to be n, which is in particular big O of n. And so the total space complexity is big O of n, right? So our Fibonacci example, not only does it have an exponential time complexity, it also has a linear space complexity. Does that make sense? Before we move on to a different example. All right. I'm going to move on. Okay, so this is kind of a canonical example anytime you talk about recursive algorithms, right? This is the Towers of Hanoi. I'm going to present this in maybe a slightly different way than you might have seen it presented, but the problem statement or the puzzle statement or whatever is as follows. We have 3 stacks, which we're going to call towers, to maybe have some kind of like physical model for them. 3 stacks. One stack starts with n elements called disks that are sorted. The other 2 stacks start empty. I'm going to call them A, B, and C, and we're going to say like A starts with n different disks on it. And then the problem statement is if the only operations we have access to are push and pop, how do we move all the disks from, let's say, stack A to stack C while ensuring that every stack stays sorted in between, right? If we didn't care about the sorted thing, we could just pop from A and push to C, pop from A and push to C. But if you remember, stacks kind of like invert the order as they push and pop, right? It's last in, first out. And so if we just did that, then C would end up sorted backwards, which is not what we want, right? So that's the idea, right? And in particular, we want to design an algorithm that, given some input size n, produces the correct sequence of pushes and pops to transfer all n elements from A to C, or from one stack to another. All right, let's think about solving this recursively, right? Here I am going to ask for some interactivity. So um, as usual, shout out the answer, put it in the chat, and we'll these are uh, pre-baked slides. So hopefully everyone's answers are the exact same ones that I've written down, or this is going to get awkward. Uh, okay, so if we're solving something recursively, we need a base case, right? What should the base case for this be? What's like a trivial input on which we know how to solve the problem without doing any extra work? N equals 0. Okay. I'm gonna say I'm gonna say n equals 0 is not an instance of the problem because we need at least one disk for there to like be a problem to move. But they're close. One disk. Yes, perfect. When n equals 1. Um, when n equals 1, what's our trivial solution? If I've got one, yeah, pop from A and push to C, right? So if n equals 1, the base case, there's a single element, so we just pop it from A and we push it onto C. Okay, now we know how to solve a trivial problem. So now we need to know how to take a non-trivial input and break it into smaller subproblems, right? So what subproblem does this contain? What is a smaller version of this problem that if we could solve it, we could then solve the full problem? One less disk on the tower. Perfect. Yeah. So we know how to move n minus one elements, right? Then we can just move n minus one things, right? Ask some Oracle how to move n minus one disks, and then just move the last one, right? We know how to move one. If we know how to move n minus one, then we can move n minus one and then one, and that amounts to moving n, right? So uh, given that, right, also n minus one is smaller than n. And so eventually, if we start with something positive, this is going to terminate, which is good, right? So given that, we can design our recursive algorithm as follows, right? Assuming we start with n elements on A, we want to move them all from A to C. We can start by moving n minus one elements from A to B and use C as like the uh, intermediate tower in between. That's a recursive call. Now we've got one thing left on A, so we directly move the one thing from A to C. That's our base case. We know how to do that. That's trivial. And then finally, we take the n minus one elements that we put on B and move them to C using A as the intermediate. That's another recursive call, right? Here's like an illustration. Again, I stole this figure from the slides. Professor Coe and Professor Johnson. Okay, so we've got a bunch of things on A. We start by moving all but the bottom one onto B. Then we move the bottom one from A to C. Then we move all of them from B onto C, right? And so the first step is that recursive step. Then we've got our base case in the middle, and we've got another recursive call on the bottom. All right. We're gonna look at some code for this, right? Tower move. If I've got a number of disks, I've got a source stack, a destination stack, and our like intermediate stack or whatever. I start by checking to see if I'm in my base case. If I am, if the number of disks is 1, then I pop from the source and push it onto the destination, and I return. Otherwise, I recursively call tower move with n minus 1 from source to intermediate. Then I move from source to destination, and then I recursively call on n minus 1 from intermediate to destination, right? This is the same thing that we talked about on the last slide, but now it's code. So in particular, you can see we've got a guard against our base case, right? So we've got an if statement that checks to see if we're in the base case. If we are, we just solve the problem as we know how to. We solve like the trivial version of the problem. And then we've got our recursive case instead, if we're not in the base case, right? So here I've got a recursive call, move n-1 disks to the intermediate, move the bottom, and move n-1 to the destination. It turns out this has a time complexity of 2 to the n as well, and a space complexity of big O of n. As a heuristic, if a recursive function makes k recursive calls every time, and has a maximum depth, like maximum recursion depth of n, then you'll see the time complexity is something like big O of k to the n, and the space complexity is big O of n, right? The maximum depth. Yeah. So given that, if you remember from Friday, exponential time complexity is often not what we want, right? And then the space complexity, big O of n, is also a lot of times not great, especially because the constant in front of n, or like the coefficient in front of n, might be really big because it's like the number of stack frames we have, and each stack frame is necessarily going to have like space for the return address and space for all the locals and space for all the parameters and space for like whatever else we might allocate there. And so it's going to be like non-trivial, right? It's going to be kind of big. And so if we've got 100 stack frames, that's a lot of memory. So recursion is a great way to like think about designing an algorithm, or like take a first crack at designing an algorithm, right? You can look at a problem, break it into smaller problems, and think about how you could like solve all of those recursively. But very often, if you just write that recursive algorithm in code, you will end up with something that looks exponential, right? And so for the next few slides, we're going to talk about ways to somehow improve that, somehow make that better, right? So first of all, one way to quote unquote fix recursion is convert it to iteration, right? So sometimes it's possible to convert a recursive function into an iterative function just by implementing the call stack in software. So what do I mean by that? We can create an empty stack, right? We know how to create a stack data structure. So we just create a stack and we push the function's parameters onto the stack, and then write a while loop while the stack is not empty, pop a set of parameters, execute the body of the function with those parameters, and instead of making a recursive call, push the parameters onto the stack. Push the parameters of that recursive call onto the stack, right? And then instead of returning, we like store our return values into an accumulator. Now, this requires that whatever operation we use to combine the results of subproblems is associative. Otherwise, we can't do this, right? Otherwise, it doesn't work. The benefit here, if we can do it, right, if the thing is associative and we sort of like implement the stack in software, is we end up saving a lot on stack space, right? We no longer, even if we have like the big O complexity is the space complexity is not going to change, right? Because the depth of the recursion is still going to be the same, which means the maximum size of our software stack is still going to be the same. However, we no longer like each frame doesn't need its own set of local variables, right? If I've got n different calls to fib, or if I've got n different like recursive calls to foo or something like that, if I just wrote this as a recursive function, I would have n stack frames at the bottom of this recursion. I would have n different stack frames. Each stack frame would have its own copy of the locals of the local variables, and it would have its own copy of like the return address back to the previous one, and so on, which is a lot of space. But if I do it this way, I don't need to duplicate the local variables everywhere, right? So here's an example, right? I create a stack called the parameters. And if I'm doing like fib of 4, I push 4 onto my stack. Now, the way I'm combining the results of subproblems is adding, and addition is associative. So I guess associative in Unital, I don't know. I start total at 0. While my stack is not empty, I pop a parameter from that stack. So I pop n off of the stack, and then I just insert the body of my Fibonacci function here, right? So if n equals 0 or n equals 1, I quote unquote return n, but here returning means putting it into the accumulator, so I do total plus equals n. Otherwise, I'm in my recursive call, but instead of making a recursive call to fib, I push the parameters of that call onto the stack. So instead of calling fib of n minus 1, I push n minus 1 onto the stack, and then I push n minus 2 onto the stack, right? And then when I go back at the top of my while loop, I will pop n minus 2 off the stack. And then I'll keep executing on that until I hit the base case for that, and then I'll go around and I'll pop n minus 1, and I'll keep executing until I hit the base case for that, and then everything will be accumulated to total, and I can return total. So we've converted our recursive Fibonacci into an iterative Fibonacci. Now, worth noting, this still has a 2 to the n time complexity, right? This is still doing the same number of steps because we've just reframed the problem and we've just kind of like made the stack space explicit. But a lot of times this will use less stack space, right? In particular, like if you're writing a function that needs to have like a really or I guess the thing here is like our parameter stack can be managed on the heap, right? And so we don't have to worry about running out of stack space. We don't have to worry about a stack overflow because we can allocate like gigabytes of space and like who cares, right? It's the heap. Does that make sense? That's, I guess, maybe kind of a non-trivial transformation to talk about. So are there any questions about that? All right, cool. Let me move on. The other thing we can, or another thing we can do to quote unquote fix recursion is this thing called TCO or tail call optimization. Um, Compilers can sometimes do this for you, but you sometimes need to put in some work to make it possible, right? So tail call optimization is another way of converting recursive functions into iterative functions. This one actually has an effect on the space complexity. In particular, if the only recursive call in the function is a single recursive call in the return statement, then there's no need to keep the stack frame of a caller around, right? Because we're going to make the recursive call, return back to that return statement, and then return from that return statement back up, right? And we're not going to do any more work when we return back up, right? So we're just going to like zip all the way up the stack and just like pop everything off at once. So there's no point in keeping the calling stack frame on the stack, or the calling frame on the stack. In particular, this means that the space complexity from the stack goes down to big O of 1, right? This legitimately changes the complexity from linear to constant. This is great if and when it's possible. If stack space is something that you're concerned about, I highly encourage you to do this. Sometimes we can rewrite functions that are not tail recursive into functions that are tail recursive by using an accumulator. I'll give an example of that. The one restriction here is, again, things need to be sort of unidal and associative, and our recursive function still needs to have only one recursive call, right? It can't be like a if we're branching out twice, if we've got two recursive calls, then no matter what, after one recursive call ends, we're going to need the other one. We're going to need the calling frame around just so that we can jump into the second recursive call, right? So there's nothing we can do about that. But here's an example of turning something tail recursive. So I've got a factorial function here, right? So n factorial, if n is 0, that's my base case. I return 1. Otherwise, my recursive case is n times the factorial of n minus 1, right? So factorial of 3 is 3 times the factorial of 2, which is 3 times 2 times the factorial of 1, which is 3 times 2 times 1 times the factorial of 0, which is 1. That's 3 times 2 times 1 times 1, which is 6. The factorial of 3 is 6, right? Factorial, great. Now you'll notice that our function has a single recursive call, right? Factorial calls factorial exactly once. However, this is not a tail recursive call. Why is this not tail recursive? And we want to point that out. Because of n, exactly. Because the last thing I do in this function is not call factorial. It's not called the like factorial of n minus 1. It's take that return value and multiply it by n, right? So the thing I'm returning is not the result of a recursive call, it's the result of a multiply. So this is not tail recursive. However, we can convert this into something that is tail recursive, right? So I can write this factorial helper function, which I'm going to call underscore factorial. It's going to take int n, and it's going to take an accumulator that we sort of thread through it. If n is 0, then we return the accumulator. That's our base case. Otherwise, we return factorial of n minus 1 and pass in a new accumulator, which is n times the old accumulator, right? And so now the thing that I'm returning is the result of a recursive call. So this is now tail recursive. And then of course, my actual factorial function just takes n and then calls the helper with n and starts the accumulator at 1, right? So now you can think about like factorial of 3 is helper factorial of 3 comma 1, which is helper factorial of 2 comma 3, which is helper factorial of 1 comma 6, which is helper factorial of 0 comma 6, which is 6. And so factorial of 3 is 6, right? This is now tail recursive. At this point, many compilers will happily optimize this away for us, and we'll turn the so I guess first of all, this first implementation of factorial that I have on the top left, right? It has a maximum recursive depth of n, and it has a space complexity of O of n, and it has a time complexity of O of n as well. Hopefully you should be able to convince yourself of that. I'm not going to draw out a call tree. Yes, this only saves on space complexity. That's correct. It's still just as time complex. Yep. But yeah, so we go from time complexity of O of n and space complexity of O of n to transforming it into this tail recursive thing. Now, naively, our tail recursive implementation still has an O of n space complexity because it's still recursive and it still has a maximum depth of n. However, many compilers will automatically take care of this for you. Some won't. If we wanted to, we could explicitly transform it into something iterative ourselves, right? So now I start accumulator at 1, while n is not 0. I multiply it into the accumulator, and then I decrement n. And then I forgot to return the accumulator at the end or whatever. But now this is iterative. It's computing the same thing as the tail recursive version on the bottom left, but there's no recursive calls anymore, right? So there's no extra stack space allocated, and the only like local variables that I have are like int n and int accumulator. And so it's a constant space complexity. This has had like an actual effect on our space complexity. Does that make sense? Sweet. All right. I'm going to move on to dynamic programming. We'll probably talk about dynamic programming more in detail at a later point in the semester. I know past semesters haven't really covered it. I think it's very interesting and I think it's worth talking about. So I'm going to bring it up here. And then if we have time or if it fits into the syllabus somewhere else, I'll talk about it in more detail. But dynamic programming is in general a way to fix the time complexity issue of recursive algorithms, right? So it's not a specific algorithm. It's a sort of technique for designing algorithms. So it's like recursion, right? It's like a way of thinking about a problem so that you can design an algorithm for it. And again, we'll maybe talk more about it later. Um, so if you remember from our Fibonacci implementation, um, we had this like uh, we had this 2 to the n complexity because every call spawns 2 recursive calls and it goes out to a depth of n, so it's 2 to the n, right? Um, but there's this like thing that we're doubling up on, right? Fib4 calls 3, which calls 2, but Fib4 later also calls 2 itself, right? There's 2 different calls to Fib2. And it's very unlikely that the value of the second Fibonacci number changes between calls, right? Um, but our implementation fully computes it every time, right? Now, Fib2 is maybe not that much work to do, but like if we look at the 100th Fibonacci number, right, it's going to ask for the 99th and the 98th. And the 99th is going to look at the 98th and the 97th. And so now we're computing the 98th Fibonacci number twice. But then they're all also going to compute the 97th Fibonacci number like 3 times. And so like every sort of there's a whole bunch of like extra work that we're doing, just like recomputing the same things, right? So instead of wasting time recomputing the same thing over and over again, we can think about caching it instead, right? So when Fib3 calls Fib2, it somehow saves the return value of Fib2. And then later on, when Fib4 goes to call Fib2, it doesn't bother actually running the function because it notices that we already know the value of Fib2, and so it just uses that cached value, right? Making that second call to Fib2 constant time instead of whatever it normally would be. So this is good for when you've got a recursive algorithm with a bunch of sub-problems, but the sub-problems share a lot of work in between them, right? So for example, finding the shortest path on a graph. Again, we'll talk more about this when we get to graphs and like search algorithms and stuff like that. But the shortest path from A to C, if you've got a point along that shortest path, it is necessarily the shortest path from that midpoint. There's this sort of like repeated work. There's this like shared work thing when you're looking at shortest paths, right? So here's a dynamic programming version of our Fibonacci. So we start by allocating space for n+1. We start by allocating a cache, right, which I'm going to call fibs. It's going to have n+1 elements because we're going from 0 to n. And then I loop from 0 to n. If it's my base case, then I just write the base case. Otherwise, if it's my base case, then I compute the base case as just 0 or 1, and I save that to the cache. Otherwise, I check the cache for my recursive calls and compute those. And just use those cached values, add them up, and then cache that new result. And at the end, I just return the thing that I care about, which is fibs of n, right? So the new time complexity is now just big O of n. The space complexity, of course, is still big O of n, but now it's because we're explicitly allocating this cache and not because we're using stack space. But it's still big O of n. Now, this only works because there's a lot of repeated like duplicate effort that we can save smaller like solutions to, and then we don't have to recalculate them. This also works great because we have like a constant time way of mapping keys to values, right? So here the key is the index and the value is the ith Fibonacci number. And that's fine because it can all be packed into a dense array. If instead we had to do this in like a linked list or something like that, then like looking up fibs of I-1 or fibs of I-2 would be linear time. And so this whole thing would be O of n squared instead of O of n. In general, if the thing you have can't be indexed into an array, you can still often use dynamic programming techniques, but you need to use like sets or hash maps to do those. And those are data structures that we will talk about much later in the semester. But that's kind of a little bit about dynamic programming. Conveniently, that is the end of my slides. And that is also a minute after class is supposed to end. So are there any last minute questions on stuff? If not, you are all free to go. Please remember to fill out the attendance poll on Brightspace. And remember that you've got a problem set due this coming Friday. If there's more questions, I am happy to stick around and answer them, but I am going to turn the recording off.